So lecture number 15. So today's topic is interesting and a new light on the vector space. It's called non-linear space. Vector space is sometimes called linear space. It's a non-linear space and inner product space. So we'll see in one by one what is inner product, what is norm, and what is the connection of this with topological space or geometry or in Rn, Euclidean space. So distance with distance or metric. Now this is slightly is not vector space thing. It is a different form. It is actually is a topology. Topology means geometry. Geometry, a generalized concept of geometry is topology. Generalized concept of Rn is topological space. Now the important concept till now we have this concept is not introduced in our linear algebra classes. This is distance. Distance is the is important, very important concept. So if there is a set and we have two elements on the set x and y, what do you mean by the distance? Distance is a very important because in R or in our real life situation in R3 is a real life situation. Also in R2 in Euclidean geometry we see what is the distance. What is the distance? So what is the distance in R? What is the distance in R? So we know the distance between 2 points in R is just distance. Say what is distance? This is like a function. Is take two input and give one output. So dxy. So distance is a function. If it is a distance on the space S is a set, non-empty set, then distance is actually S cross S to a real number. Actually, is can't be negative, so it is a positive real number in 0. You can write codomain as the whole R. Now this is greater than or equal to 0. So distance between two things is greater than or equal to 0, and we know in R the distance is just a mod of x minus y. So mod of x minus y is the distance in R. And obviously distance in R2, what is a distance in R2 is if x1, x2 is a 1 point, say it is x, and y is another point, y1, y2, where y1, y2, x1, x2 are in R. So x and y is R2. So x and y in R2, the distance between this x and y, we know this our real life distance. There are several distances, but our real life distance is root over x1 minus y1 whole square plus x2 minus y2 square. Now this is natural. Similarly for R3, it is just x1 minus x1, x2, x3, y1, y2, y2. Distance between these 2 points is x1 minus y1 square plus x2 minus y2 square plus x3 minus y3 whole square root over of all this sum. Now this when is R is there, just R is a set, just nothing, no structure is there. It's just a set. The elements of R 1, 2, 3, 4. 1 maybe some cow, 2 is a horse, 3 is a book, maybe something like that. But we slowly introduce some structure on that. What is the first thing? We first introduce addition on this R, addition. Then we define some inverse thing on addition. Then identity element, the subtraction. Subtraction basically addition. The 4 operation, actually there are actually 2 operations there. Then we introduce multiplication. Now we introduce multiplication using addition for natural number, but for real number, we can't introduce this multiplication using addition. Pi into e. What do you mean by pi into e? You can't describe in terms of addition. So we introduce one more operation, which is called multiplication, and we know this R is filled with these 2 operations. We fill means some satisfy some conditions. Now there is something extra on R. What is that? This is ordering. This is a partial ordering. We introduce one more structure. So something is less than this, 2 is less than 3, less than or equal to 3, something like that. Now, once you introduce this This is a partial order. We can prove that is a partial order, and what are that the properties of the condition of the partial order, and obviously there is a relationship. There is some result involving this order and addition also. Something, if a less than or equal to b, then a plus c less than or equal to b plus c. That we know from our school in class 4-5. That if a less than or equal to b, then a plus c less than or equal to b plus c. You can't prove that. This is action. So there's some action, and this is called ordered field. Now all this is only some operation, algebraic operation. Now this all structure called algebraic structure. But now we are going to introduce a topological structure. Now there is nothing distance here. Now, if we can do this, okay, forget about addition, multiplication, and ordering. We just introduce a distance on R. Forget this addition. We don't know what is 2 plus 2. Now it is what 2 plus 2 is meaningless to us. We don't know what is plus, what is addition, what is multiplication. But we know only just distance between two elements, 5 and 6. So distance between 5 and 6. So how do you define distance factors? So then the mod of, you have to introduce then minus. But we can easily say that, okay, we forget about the addition or multiplication. We can just say, okay, distance between 5 and 6 is 1. How it is given is minus mod of minus 5 minus 6. Forget about this. I just introduce distance between 5 and 6 is 1. Distance between 7 and 9 is 2. How do you how do you get this? Forget about this. We have no idea of addition, the difference. We just list all this distance between this and this and this. So we just introduce distance. Remember, we introduce distance. We can introduce distance without the help of addition or the subtraction. It's just a function. It's a function from R cross R to R plus union 0. It's just a function. Now this introduces a topology. It's called distance means topology. There's a geometrical structure. Now we are going to combine these ideas, algebraic structure with this topological structure. Now this is the first thing. We are combining this algebraic structure with this geometrical structure. With distance between xy is coming from an algebraic operation. That is the interesting thing. Now, algebraic topological structure is coming from an algebraic counterpart. X minus y is just algebra. But this x minus y is x minus y means x plus minus y. It's just simple algebra. X means is a lion, y is a cow, minus y is a dog. So lion minus cow is just lion plus dog, something like that. And mod of this is, again, this mod thing is just minus of 3 means 3. So mod of, say, cow is a tiger, something like that. So this is purely algebraic. Now this purely algebraic thing is going to be a geometry if we structure like that. If we define the distance like this number, just that number, that x minus y, this is a purely algebraic thing. And that's why this mod has the the x minus y is just algebraic thing. But once you get this mod, this basically have some geometric idea. That's this mod. The beauty of this, the distance, actually the idea of concept of distance, or that beauty, the magic came from not from this x minus y. It basically came from this mod thing. So that means your geometry on that. If x minus x, you reflect on that x. So mod of minus x is mod of x. So this is actually or x. It is x. This is coming from geometry. If you just write cow, lion, tiger, then this geometry, you can't. This is a symmetry thing. This is a symmetrical, or it is just a reflection about origin. This idea, this mod idea, is actually coming from this geometry. Otherwise, x minus y is just a algebraic part. X minus y is a number, which is just an algebra. So this is the beauty of this mod. Mod is the magic thing which actually introduced this topology on R. Now this is called distance, and once this distance is introduced on R, then we call it is a Euclidean space E. So What is Euclidean space? Euclidean space is, as I said, this is a real line. This is a real number, as I said, with a Euclidean distance. This is called Euclidean distance. There are several distances. Just distance is called Euclidean distance. Now, similarly for Rn, in general, Rn, we have a Euclidean distance. Clearly, this Euclidean distance is between these two numbers, x and y. At the coordinate of x is x1 is to xn, and the coordinate of y is y1 y2 yn. And we know this is sum over xi minus yi. This is by definition, okay? So I equal to 1 to n equal to the power half. So by definition, this is the distance. And actually, what do you mean by distance? This is called n-dimensional Euclidean space. We write En. So once you write En, what is the difference between En and Rn? As I said, they're equal, but Rn has no geometric structure, no topology. Un has topology. Still now we are not using that vector space thing. We are not this algebraic part. So what is distance? Distance has actually three things. Distance must be greater than or equal to 0. It's a real number greater than or equal to 0. Distance between any two numbers. Number 1 must be greater than or equal to 0. Next, the distance between x and y is 0 if and only if x equal to y. If two numbers are distinct, the distance is positive. And if they are equal, the distance is 0. And the third one is the most important part. This is called triangle inequality. Distance between x and y and z is less than or equal to distance between x and z. This is called triangle inequality. Now this Rn, or in R or R3, this distance, Euclidean distance, satisfies this. You can usually check this satisfies this, all these three properties. The first two are trivial, third one is slightly complicated. It's calculating. Now, once we can do this distance not only for Rn, we can in complex number, we can do in any set. If we can introduce a distance sometimes called metric. Distance in Rn, in R3 up to, for in general, in arbitrary or abstract set, we say it is metric. Metrics means it's a distance, some sort of distance. The more general term distance is metric. So once you have if we can introduce a metric on a non-empty set, then this whole thing, this set as well as that metric is called the metric space. So metric space is a non-empty set together with a metric. What is metric? Metric is a function d which satisfies the following three conditions. And we'll see in our real analysis course or metrics book, when we go into this functional analysis, we will see several distance metric, but just we consider only this Euclidean metric or Euclidean distance. Now again, so this R has some extra thing. So distance is there. So we can introduce distance. Now in a vector space, so say there is a set, and this set is a vector space over some field R or maybe C or maybe in general field. That means we have one more extra operation, vector addition and a scalar multiplication. We have these two on this set. We introduce already. Now if we introduce distance on that same vector space, now this is called linear space. Is vector space is a linear space. Now we are introducing a metric or a distance or like topology on this linear space or vector space. Now we can do this. We can do this for a general vector space also. For metric space of all matrix, n cross n matrix or GLN, special linear group SLN. But for real number or R2, especially in R2, not in R2 or R3, this is a special type of, is one more idea, is called direction. Not only the distance, the sort of direction is also one important concept in R3 or R2. What is actually meant by direction? Direction actually comes from this idea called angle. This angle actually gives some idea of the directions. So not only the distance, the direction is also important in R3 or R2. So, but in the metric, in distance or a metric, in a metric space, the idea of angle is not there. So idea is angle is coming from this idea is called inner product. once we have the inner product thing, we have the idea on angle. So inner product is introduce a distance as well as a concept of angle. So what is inner product? Formally, inner product is a, if it is a vector field and V is a vector space. Now, inner product, by the way, this once the distance, defined distance need not to be a vector space. It's just any set. But to define norm, define inner product, you need a vector space. Remember that. In general set, you can't define in vectors inner product. Why? It came later. So this is just an inner product. This is just a function, like a function. Sometimes is called like that, or some authors say this dot means is something, some function. We also write in this form. We know the fx is not the function, f is the function, but till with this called argument. What to introduce that argument thing. So how do you write e to the power x? So if I ask how do you write the e to the power x function? So one thing is, okay, f is the function such that fx equal to e to the power. That is slightly tedious. So you better you write this. This is the function. This is the function. This argument has dot. That means you take the input there. You put you place that dot by the input. So that means is actually function from V cross V. You take two input, alpha and beta. So if you take two input alpha and beta from V, that means alpha and beta two vector. Why vector is needed? This is a norm. This output is a norm which satisfy the condition such that now if alpha plus beta with this gamma is just alpha plus gamma, alpha gamma inner product plus beta gamma inner product. This, by the way, this field we are take this field as just real or complex. Real or complex. Real or complex. Now this in general set, this plus is not there. So you need a vector space. You have to define this addition thing. Otherwise, this inner product, in the definition of inner product, addition is already there. So to define inner product, you need a vector space, but define a distance. You don't need a vector. No need of vector space. No need of addition. Just a set of some stations, and distance between Barasat to Hridaypur is say 5. The fare is the 5 rupees. So it is 5. Distance from Barasat to Shialda is 10. So no need of addition. Barasat plus Hridaypur is some station. But to introduce inner product, that's why the idea of direction. Okay, this angle. In general abstract set, the distance concept is there, but till the angle concept is not there. Number one, this is this, and then if any scalar, see the scalar, or this is the field scalar. You always in term, if I say the scalar, that means a real or complex. Scalar, then this with beta is just C into alpha beta, and this one is very important. This is beta alpha. If we just interchange, then it is alpha beta for real, but for complex it's just a conjugate. So if it's real, no need of this conjugate thing is same. The conjugate of x is x. The last one is this. The alpha is always positive if alpha not equal to 0. For 0 it is 0, 0 to 0. You can prove it is inner product between 0, 0 is 0 using that property A. You can prove it. So this for the inner product is like a function from V cross V to real number, or that complex number in general field, not a general field, real or complex, with this together with this 4 property. This is called inner product. Now, inner product may not be defined in any in general space, may not be defined. So it is now we are restricted our thing. So that this general set is a huge thing, a complete thing. Now we are introducing some addition. So vector space, we are just still we have a huge class of vector space. But once you in the R or Rn, that is a very restricted class. Now we are restricted our thing. Now we are defining distance. So we are restricted our this whole vector space concept. Now we are again restricted with inner product. So in inner product, maybe some vector space is there. We can't define inner product, but we can define a distance. So so is the inner product space is a metric space? That's the question. If we define inner product, is it a metric? Yes, the inner product. Once you give a inner product, the distance is just, you can just construct the distance from the inner product. But this needs another thing, is called norm, via norm. So maybe such a thing, there's a norm is defined there in a linear space. If just norm is defined, may not be inner product is defined. The norm is defined. Is norm defined in a linear space, then it is called norm linear space. So norm linear space is a vector space including a norm together with a norm. So again, we can go. How do you go from inner product to norm? Later we'll see. By the way, the norm also has some property. What is the property of the norm? Again, norm is not, is just only one element. You need a, sometimes norm is this function. So you put introduce one single element. Now here is a two ordered pair x1. Now it is only one. Norm x. What is this? Again, norm of x must be greater than or equal to 0. Number one. Number two, something like distance. Norm of x equal to 0 if and only if x equal to 0. Remember, this x equal to 0 is meaningful because you are dealing with vector space. Since we are dealing with vector space, there is a null vector here. So we can talk about x equal to 0. Otherwise, in general set, we can't say x equal to 0. So to introduce norm, also you need this. Now, next one is very important, that norm of x plus y is less than or equal to norm of x. It's triangle inequality. You can write norm of x minus y. Norm of x minus y is less than or equal to norm of x plus norm. This triangle inequality. So basically, this is just coming from the distance. It's the same idea of distance. So we have several terms now. We have distance, that means the metric, norm, inner product, all these things. Now, what is the relationship between all this? One more thing is, sorry, since it's a vector space, so alpha into x, this norm should be mod alpha norm of x. So we have a result on norm using addition, using a multiplication also. Now, the distance actually give a more general topological space. What is topological space? Topological space basically deals with some open set. You know, in R or Rn, R2 is the best thing to visualize. So is R2, you know, some what is called the open set. What do you mean by open set? So the topological space means is just declare the all open set. Now in R2, the open set are coming from the distance. So in R2, we have a concept of distance, and using that idea of distance, we are defining what are the open set. What are the set is open? So we know what is set is open. So to define open set, if say A is a subset of R2, and if a element on A in A is called interior point of A, we know it's called interior point. X is interior point, and interior point if there exists some delta positive So if there is some delta positive, such that if you take the neighborhood of this is called neighborhood, or sometimes called ball. What is the neighborhood? That means the set of all y in R2, set of all y in R2. So that means a subset of R2, such that this y is the distance between y and x is not more than delta, no more than delta. Is a less than delta, strictly less than delta. It can't be equal to delta, equal to the closed ball. So this is called a ball delta radius. Actually, disk in R2 is a disk. This is also called ball delta neighborhood of x. Now, this obviously is a subset of R2. If it is a subset of A for some delta, maybe small delta, then this A is called interior. That means A is such a point such that if you go slightly around that A, it's still in this your in territory, in your own territory. A is your territory. But some points are there, maybe in called boundary. If you whatever is small delta you take, is always you go outside that. It's called the boundary thing. So this is the idea of topology. And if every point of this A is interior point, then A is called open set. We know every point of A is the interior point, then it's called open set. Now, this idea coming from this mode thing, that means distance. In more general metric space, we can just replace this by this more general distance in Rn, or in maybe Cn, or maybe in general vector space, or maybe in general topological metric space. May not be a vector space there, because to define distance between x, y, no need of this addition or scalar multiplication or this difference. We have no need. Now this is actually this open set definition is coming from the metric when the metric space is there, but we can define in the other way. We can say, okay, we have a set, non-empty set, and we are declared that these are the open set, and this set of all open set is called the topology. Collection of all open sets is called the topology. And obviously, this you can't take any arbitrary collection. You need some restriction. What is the restriction? No, the one restriction is you have to take the whole set as a open set. You have to take the phi set as open set. And if you take A1, A2, AN, not AN is arbitrary collection of open set, not only the countable, maybe uncountable, arbitrary collection of open set, the union, arbitrary union is also open set. You can prove it using distance or metric, but forget about the metric. You have no metric on that. You have just a set, and you just declare this sum set as a open set under some restriction. This is called topological space. Now, this is a question. Obviously, a metric space is a topological space. But is every topological space, can we define a metric on that such that that metric introduces the same topology? Answer is no, because topological space is more general thing. The topological space, you can't define a metric. You can define a metric, but that metric will not give that open set what is defined in the topological space. Different set of metric open set. Now there are some condition. How do you know the topological space has a metric which induce that same? This is called metrizable. Once a topological space has a metric, then it's called metrizable space. We'll see in the topology class, not in the real analysis. It will be topology class. Okay, forget about this all this topology. You just come down to this distance. Now, a norm can define a distance. How norm can define a distance? So distance define a topology. Every topology may not define a distance. So how norm can define a distance? You have a norm. So to define distance is just very easy. Is this? This is just, if you can easily check that if you have the norm, you know the norm, and you have the properties of the norm, you have to prove the properties of distance. On the other way, so you can define distance from the norm. Similarly, in the other way, you can define norm from the inner product. That's also clear from this, and you can easily prove that this thing if you have a norm, if you have an inner product, using that inner product axioms, you can prove that this root over inner product xs is a norm. You can prove that. And so from that you can define a distance, and from that you can define a topological space. So in a vector space, if you can define an inner product, is actually creates a topological space. It's creates topology. It creates some open set on this whole vector space. Obviously, there is a more general thing. It's called topological vector space. In that case, the vector space using in the vector space, we are declaring some set as a open, and that may not be came from induced from a norm, or may not be came from a inner product, or may not be came from a distance at all. So we can't define a distance such that distance on the vector space induce the same topological space, same topology. No, may not be. In general, it's called topological vector space. There's a vector space with together with pre-declared some open set. We declared this as open set under some restriction with some that conditions, that union and other thing. Now, this norm into the inner product introduce a norm introduce a distance, and this introduce a topology. And again, this a topological space is metrizable. Then we have a metric. We can define the metric. Then the question: if you have a metric space, how do you know this is coming from a norm? How do you know? How do you know this came from a norm? This is called parallelogram law. If you have a norm thing, you can easily prove that. This is very easy to show. It's basically in R2 is just an application of Apollonius theorem. It's actually sum of two square of the diagonals is just twice of this, the square of the sides, twice of the sum of the square of the side. You know this result in geometry. You can easily prove that using this. Once it's coming from the inner product, sorry, it is coming from the inner product. If it is coming from the inner product, then this norm has this property. But if some norm is not coming from the inner product, then this parallelogram identity is not true, it is violated. So if you just check. If you have a norm is there, you have a norm, you don't know if this is came from a inner product or not. You just check whether the parallelogram law is hold or not. If it's hold, then you can say, okay, this norm actually came from inner product, and you can define that inner product and show that this inner product induces that norm. Again, this needs a vector space because we are adding two numbers. We are subtracting two numbers. Similarly, there is a thing from how do you know a distance came from a norm. There is one more thing we have to leave it. So there is something is there. How do you know a topology come from a metric? How do you know a metric came from a norm, and how do you know a norm came from an inner product? So if you have a norms linear space where that parallelogram law is not true, you can say this is just a norm linear space. It can't be a inner product space. So this is very interesting thing. And now this is a concept of angle now. How do you relate this inner product with the angle? Now this is a came to relate this inner product with the angles. We have inner product. From inner product we can define a norm, and okay, x and y are two non-zero vector. It's a vector space again. Remember, it's a vector space, and it's a non-zero vector, so norm is non-zero, positive. And cos inverse of this, we define this as the angle between x and y. But again, question: how do you know that this cos inverse is defined? Because to define something cos inverse, you need this quantity must be lies between -1 and 1, unless the cos inverse is not defined. It may be abstract set. Remember, it may be abstract set. It may be a set of functions, set of matrix, set of random variables. In Rn, the one natural inner product is a dot product. X1 is to xn, y1 to yn. The natural inner product is a dot product. x1 y1 plus x2 y2. And we know in that case, if x1 is to xn and y1 to yn, and the inner product is x1 y1 plus x2 y2 dot dot xn yn, then this is came from the Cauchy-Schwarz inequality. We know from the Cauchy-Schwarz inequality, this is less than or equal to greater than equal to minus 1 or less than equal to 1. But remember, the inner product is may not be came from a dot product. It may not be eventually a Rn from the Rn. The set may be a collection of all differentiable function like that, set of all differentiable function, and you are defined vectors of addition over that set of differential function. So in that case, dot product of these two function is meaningless. You have to define some inner product in other way. Norm in that once you define the inner product, you define the norm. Now you have to prove the Cauchy-Schwarz type of inequality. Then also here is the Cauchy-Schwarz inequality in general inner product space. So you can general inner product space, you can prove that this quantity lies between minus 1 to 1, and this is called Cauchy-Schwarz inequality for general inner product space. So once we have this Cauchy-Schwarz inequality in general inner product space, we have this angle, idea of angle. And by the way, this idea of angle actually match with our angle idea in R3 or R2. It is just a generalization. In R2, in Euclidean space, if you define theta like cos inverse this, you will get the exactly the same thing, same angle as we are learning in our class 6. That angle 60 degree, 90 degree, pi by 2. The same thing we will get. And cos inverse is always, we know that how do you define this cos inverse? Remember, this quantity is a real number, that neuron product by this. And obviously the idea of perpendicularity is just the theta equal to pi by 2. That means your cos theta equal to 0. That means your inner product, if the inner product is 0, we'll say this two vectors are perpendicular. Now we have introduced the idea of perpendicularity in a general inner product space. So that's all in this lecture.